Hi, everyone. Welcome back to our second session during our event today. It's my pleasure to introduce you to Angelo Corsaro. Angelo is Chief Technology Officer at Adalink Technologies. And in today's session, Angelo will share with us more insights about the Zenoh protocol. Angelo, the stage is yours.
Okay, thank you very much. And I guess you can see my screen, right?
We can see your screen.
Okay, perfect. So let's get started. Okay, so something that IT system used to deal with, and data in motion was something that used to be dealt with OT systems, so operational systems, and the two worlds were living happily, separated. But things are changing, and how are things changing? Well, if you look at the enterprise world, they realize that they need to. There is a tendency toward adopting reactive architecture, and as a consequence, having to deal more and more with data at rest and data in motion, ideally in a unified manner. And if we look at what is happening in the OT world, there is obviously a convergence between OT and IT that is requiring also us to be able to integrate again and deal in as much as a uniform manner with data at rest as well as data in motion. Okay. So if we also then put into the equation the rise of industrial IoT, edge and fog computing, we have yet another dimension, which is, well, you know what, we need to deal with data at rest, data in motion, ideally in a uniform manner, but we have to deal now with all the heterogeneity that comes with edge, fog computing, industrial Internet of Things, and we need to deal with the decentralization and the necessity for decentralization, the necessity for dealing with maintaining data locally, for computing data locally, as opposed to potentially centralize everything toward a data center. And as a consequence, we would want to leverage this decentralization to take advantage of locality and local resources, but without losing something that is essential to maintain the system manageable, which is location transparency in spite of geo-distribution. Now, many people, when they try to solve this problem, they try to adopt a cloud-centric solution. So that's where you put all the data. That's what you use for essentially integrating data in motion and data at rest, and that's what you use to gain some kind of location transparency. But that works only so far, because what if all of a sudden you have multiple potentially data lakes, and also you want to maintain some data locally, besides wanting to integrate data in motion and data at rest, and having to deal once again with devices that can go from a traditional server down to a microcontroller. So how do you do it? How do we do it while maintaining, once again, location transparency and having the right level of efficiency, both in terms of space as well as in terms of time and network overhead? And once again, decentralization becomes quite important because, for latency, throughput, confidentiality, ideally, we would want to maintain the data there where it makes sense, which most of the time is where it is created, and then have an infrastructure that is sufficiently intelligent to allow us to run distributed queries to go and fetch data where it needs to be, so where data is stored, and transparently consolidate that to us. So if you want to address this problem, once again, today you really have two choices. Either you embrace the cloud-centric paradigm, but then you have something to pay back, which is privacy, potentially performance, and efficiency implications, or you get in a very complicated and error-prone patchwork design with multiple protocols sticking together, messaging or pub/sub with storages in order to be able to address the requirement that you have end-to-end, typically spanning from embedded constraint devices to potentially regular hardware like 64-bit processor or ARM-A as opposed to ARM-M or even smaller. So this is the landscape that motivated us to bring Zenoh to all of you. So what is Zenoh? Zenoh is a technology, as you will see, that unifies data in motion, data in use, and data rest, as well as computation. It provides one protocol that blends traditional pub/sub with distributed queries, as we will see, while retaining a level of time and space efficiency that is, as you will see with your eyes, completely beyond any of the mainstream stacks. As I will show you, we have 4 bytes, so 4 bytes wire overhead for user data. Additionally, on top of this very efficient protocol, it provides you with a very simple to use API for pub/sub, as well as an opinionated, as we will see, implementation of geo-distributed data storage and geo-distributed computation, and we'll try to understand what that means. In terms of a stack, the Zenoh technology is really made by 2 layers. We have Zenoh once again, which is the first API that you typically see to do pub/sub, to do distributed queries, that deals with data representation and transcoding, that provides you with a uniform way of representing, as we will see, queries in spite of potentially integrating with heterogeneous storage technologies. So that's really what Zenoh provides you, as well with some pre-cooked consistency algorithm for your geo-distributed storages. And all of this builds on top of our networking protocol, which is Xeno Net, which is a networking layer, which again is capable of running above a data link. So you could put these on top of BLE, you can put these on top of plain Ethernet, but you can put it on top of IP or on top of a UDP or a TCP. The key point here is that Xeno Net does its own routing if necessary, okay? And the only thing that requires from the lower layer is just a link protocol that is able to send best effort messages on the other side of the link. That's all that Xeno Net requires. And again, everything else is provided if necessary, okay? So if we zoom for a moment on Xeno Net, Xeno Net is really made by 3 little protocols, okay? There is one protocol, which is our scouting, and that's a pluggable discovery service, okay? So depending on the network you're sitting on, the scouting implementation might differ, okay? For instance, if we're sitting on an IP network, we might decide to do scouting through using, let's say, multicast. If multicast is a possibility, we could use an LDAP service or whatever. There are multiple ways of implementing scouting. If we are sitting on top of Bluetooth, then we can use BLE or traditional Bluetooth built-in discovery to do Xeno scouting, okay? And then the other, let's say, mini protocol of Xeno Net is the session protocol. This provides us with an abstraction which is independent of, let's say, the underlying layers, okay? That gives the higher level protocol, so the Xeno Net protocol, an ordered, best effort, and reliable, as well as reliable channel with the illusion of unlimited MTU. In other terms, okay, the Xeno Net protocol is able to work on a session whose implementation is specific of the underlying, let's say, transport mechanism, okay? And this abstraction gives us channels that are either best effort or reliable. They are in any case ordered and have ideally an infinite MTU. In other terms, it does fragmentation for you, even if the underlying transport or network doesn't support fragmentation, okay? So that's quite important. And obviously isolates the rest of the protocol from the nitty-gritty details of the specific network technology that we're using, and gives a very clean separation, as we will see, without compromising performance, which is also important. Okay, so what are the key abstraction of Xeno Net? So first of all, in Xeno Net, data is named. So we follow the tradition of named data networking, which is an initiative that started in the context of next generation internet, trying to build a series of protocols that can run without IP or on top of IP, but that doesn't suffer all the problem that IP has. So I cannot give you a full introduction on NDN, but there is a very nice site managed by the Stanford University where you can find plenty of literature of NDN and understand how Zenoh integrates some of the key benefits of NDN and goes beyond by providing also very good support for diffusing data. So, as I was saying, in the tradition of NDN protocols, data is named, and is named just by a sequence of byte arrays. And usually we call this name a key. An example here is /home, /kitchen, /sensor, /temp, where in this case, / is the separator I'm using between the byte arrays, okay? Data interest as well as intents, and intents represent the intent typically of producing some data, okay, as we will see, are expressed by means of key regular expression. So I could say that I'm interested in receiving data that matches the key expression on star C202, okay? So in that case, the star will expand to an arbitrary number of byte arrays, okay? A single star only expands to one byte array. So quite straightforward, and if you are used to URI, that should make quite a bit of sense to you. How do you select data in Xeno Net? Well, in Xeno Net, we use selector in order to identify data set. A selector is composed by a key expression, like we just saw, an optional predicate, an optional projection, and optionally a set of properties. So for instance, I could say that I would want from my home stars, so meaning in any room, for sensor temp that are in any room, those for which the temperature is greater than 25, okay? Or I could say that for my car, for the dynamics, let's say, resource, if the speed is greater than 25, I want you to project the acceleration. So just give me the acceleration. So projections are just a way of selecting attributes or a set of attributes out of your resource, pretty much like you do in databases. I'm not showing you example with properties, but you can pass to a selector also a list of properties that will be interpreted by the target of this query. So Zenoh uses the key expression portion of a selector in order to route queries to the queryable entities, as we will see, that need to answer that query. Okay, Xeno Net does not interpret nor understand the query syntax, the projection, or the properties. Those are understood and implemented by the queryable entities, and we will see that's implemented by, let's say, the user of Xeno Net, which specifically in the case of Xeno can be either you, if you're developing application at Xeno Net level, or the Xeno layer. It also provides different policies to control query consolidation, as well as completeness and potentially quorums if you want to have strong consistency as opposed to eventual consistency. So you are also able to control that. What are the key abstractions that Xeno Net provides? So those are resource, which is named data. So in other terms, a key and a value. Publisher, which is a string of values for a key expression. So once again, a publisher produces value. You cannot ask value for it. It just produces value. Visualize this with a water analogy. On a springs, there is water that comes out. Then you have subscriber, which are sink of values for key expression. So again, a sink is somewhere where the water ends up, okay? And then we are queryable. A queryable is not a spring, it's a well of values for a key expression. What does it mean? Into a well, I can go to get water, if you like this water analogy. So if you can visualize, publisher is something from which data sparkles out. A subscriber is something that wants to sink data in, and a queryable is something, and is an abstraction that allows you to tell, you know what, for the key expression, by the way, if you ask me, I will give you data whose key matches this key expression. Okay, so those are the key abstraction that we have in Xeno, and the key abstraction that we use to actually marry, I think in a very elegant way, data in motion and data at rest. The primitives that we make available are Scout, that allow you to look around for Xeno entities, and there are masks that you can use to decide what you're looking for. So that could be routers, that could be peers, or something else. Open close to open and close session, and then a series of declare and undeclared messages to declare a resource, declare a publisher, declare a subscriber, declare a queryable. So declarations are used for discovery, because Zeno has dynamic discovery, as well as for various optimization. And I'll get back giving you some hint on when those optimizations are done, okay, and what they are done for. By the way, when you declare a subscriber or a queryable, you provide also a callback that will be triggered in the case of the subscriber when there is data for the subscriber, while in the case for the queryable, this callback will be triggered when there is a query that you have to resolve. Okay? So the other primitives that are available are write, that allows you to write data for a key expression, pull, that allows you to pull data for a pull subscriber. So I actually glimpsed over it, but subscriber can be push or pull. A push subscriber receive data whenever that is produced by publisher. A pull subscriber is slightly differently. So if you have a device that is sleeping, you cannot push data. So you can say, well, I'm a subscriber, but I'm pull in the sense that the infrastructure will get the data as close as possible to you. And then whenever you wake up, you're able to pull and fetch this data from the closest place where the infrastructure could actually cache it for you. Other important things is that both push as well as pull subscriber can negotiate schedule at which or according to which the infrastructure will either schedule push or pull. Last abstraction that we make available is that of a query that will issue a distributed query and return a stream of result. So here we have an example to visualize both the data flow and the query flow. For instance, again, if we have a domotic application, a temperature sensor could be an example of a publisher, likewise a luminosity sensor, a data storage, or at least the query portion of a data storage could be a queryable. As you can imagine, if you want to implement a store, you need actually to couple a queryable with a subscriber if you want the storage to be written, right? Otherwise it will be read-only. And then a subscriber that you would use actually to express interest for data to receive in a proactive manner, okay? Yes, so I already went quickly through push and pull subscriber, and let me illustrate this with an animation. Okay, so let's assume that we have a system, and you see we have a routing network of Zeno. So obviously we are thinking of a Zeno infrastructure that might be deployed across the globe. And again, this Zeno router could run on top of an IP network, or perhaps not. Okay, so they could run on top of a data link layer that would be sufficient as well. You see from the Z that we have the device that is battery powered and go under sleep. So whenever there is a publication is distributed to interested parties, okay, so subscriber and potentially storages that take ownership for the data. And for devices that are sleeping, whenever they wake up, as you saw in the animation, they can actually pull the data that was maintained by Zeno as close as possible to the pull device. When you issue a query, the query is routed by Zeno to try to find the best set that can answer that query, and eventually data is consolidated depending on the policies that you have provided on the way back. So that's the simplest way of visualizing how Zeno works, or that Zeno Net works. In terms of reliability and ordering, Zeno really has three kinds of reliability. You can have hop-to-hop reliability, and that guarantees hop-to-hop ordering and end-to-end ordering unless you have a failure that induce a change in the routing graph. Then you can have first-to-last broker reliability. In that case, even a failure in the routing graph allows us to maintain first-to-last broker ordering, and then you can have application-to-application reliability. So for those of you that are curious to understand why we have these three flavors of reliability, is because the one that is the cheapest in terms of state that we have to maintain on application, obviously is next hop, okay? Because the only things that we need to maintain in terms of state is the reliability with one hop, the hop down the road, let's say. But for some application, end-to-end application-to-application reliability is important, and that obviously is the one that has the biggest impact in terms of memory utilization and state. But the Xeno Net protocol provides you, with a good mechanism to have the right level of trade-off. Our routing is important to understand that it is adaptive fault tolerant, and we have a self-stabilizing, decentralized a graph building algorithm. I cannot go into the details, but what matters is that this algorithm is self-healing, and we can use up to k-spanning tree to route data for both load balancing and fault tolerance, where this k can be limited by configuration. So in summary, what are the key features of Xeno Net? So it's the most wire power and memory efficient protocol because, as I mentioned, it has only 4-byte wire overhead for data. Okay, and in terms of memory footprint, the smallest implementation that we could write could fit in 300 bytes on an Arduino Uno microcontroller. It supports push-pull subscriber, publish and subscribe, as well as distributed queries. So it allows to use resource keys, but these resource keys on the wire are represented as integers. And in fact, some of the optimization that are done by our discovery and the declaration, especially declaration of resources, are precisely to do this binding between resources and integer. Notice that this binding is done automatically and is local to an application session. So you do not need to fix integers that are global to your system, because that would be a mess, would be very complicated. It supports peer-to-peer as well as routed communication, and it's just one protocol that we use for client to broker or client to router, peer-to-peer, or router-to-router communication. It has order reliable delivery and fragmentation, a minimal wire overhead of 4 bytes, and for any message, you can have user-provided attachment. So how you use those attachments, we don't care, because if you attach, let's say, attachments to data or declaration, those are provided to the other hand to the application of Xeno Net for the application to interpret. And there are lots of creative use of attachment that obviously can be made. Okay, Coding Lab. How does a Rust publisher looks like? So here you see that we use Rust Async API for Zeno. First things that you would do, you would open a session, declare a resource in this case, declare a publisher, and then just write it, okay? Then you undeclare and you close, done. This is a subscriber that uses a function, but you can also use lambdas. So once again, we open a session, we actually define the subscriber info. So in this case, it's a reliable subscriber, is not asking for agreeing a schedule. So it will be, data will be pushed as soon as it's available, because its mode is push mode, as you see here. So we'll declare the subscriber for the given resource, and then whenever data is produced, this callback will be triggered up to when we don't insert a Q in the, so a letter Q, as you see here, on the console, and then we'll be done. By the way, this is an example for our new version of Zeno, which is completely being rewritten in Rust. Yeah, and the performance I will be showing is also for the Rust version, the master of the Rust version, if you want to give it a try. So here you see performance of Zeno peer-to-peer compared to Mosquito. So in this case, in Mosquito MQTT, there is a broker. But you see that we start at 1.1, a little bit more than 1.1 million messages per second, which we maintain for size of payload between 8 and 128 bytes, and then slowly degrade up to reaching around, let's say, 250, 260,000 messages per second for 16 kilobytes, and we are around a little bit less than 500k messages for 8 kilobytes. If we look at Zeno brokered, and again, these tests are done on an Intel 64-bit i64 8-core, okay, single host. That's why that's why, for instance, the routed has fewer throughput than the peer-to-peer. I mean, it will always be the case because there is an extra hop, but if we were running this on multiple machines with a very fast network, we could compensate some of that, because running 3 processors starts getting, at least on the machine, on some CPU contention. So you see that the throughput is a little bit less, but still quite massive. And if we compare Zeno peer-to-peer with Zeno broker, we have here, so there is some difference, but it's not so big. And compared to other protocols that are also addressing constrained environment, you see that, I mean, the graph speaks. I don't need to comment the graph. If we look in terms of throughput, not just in terms of messages per second, you see that even for 8 bytes payload, we're able to push on the network up to 100 megabits per second. And that's with you are just writing data. There are some middleware that force you to explicitly batch. Here we are not doing. The application is just writing, you should maybe I don't know if I have time, but look in the distribution. It's a trivial application with a loop that writes as fast as it can. Okay, so it's not as if we are playing trick and we are writing, instead of messages of 8 byte, an array of 1,000 messages of 8 byte. No, so that's actually how smart the protocol is. And you see that we can saturate or reach a gigabit throughput already at about 128 bytes, and we get around beyond 30 gigabit per second at 16 or starting from 8K. So in terms of throughput, it's quite amazing. Okay, and it's important because, once again, recall that our routers are intended to be used for routing traffic across the internet that is aggregated and might be going on some very big pipes as well. Okay, let's move now to Zenoh. So Zenoh, as we discussed before, builds a higher level API for PubSub, distributed queries on top of Xeno Net. It provides you with data representation transcoding and an opinionated implementation with geo-distributed storage as well as distributed computed values. All of this builds on top of Xeno Net. In terms of the encoding that you can use at Zenoh level, okay, this API level, we support JSON properties, relational data representation row, and transcoding for all of those. And the canonical query syntax that we use is based on URI syntax. Okay. So our geo-distributed storage has a storage backend plugin API, and currently we support backends for main memory, MySQL, MariaDB, PostgreSQL, SQLite, and a time series such as InfluxDB. Once again, we do automatic transcoding for data across different formats, as well as we adapt query, because when you issue a query in Zenoh, you issue it using URI-like queries, but then depending on where the data is stored, you might be hitting an SQL storage or main memory. And it's Zenoh, or the plugin for that backend, that does the on-the-fly interpretation and translation of the query, perhaps into an SQL query. Okay. In terms of consistency, by default, our geo-distributed storage works under eventual consistency, but you have mechanisms and primitives that allow you to do quorum and thus stronger consistency if you want. And the storage alignment is provided by infrastructure. So that's how the geo-distributed storage works. You have storages that can express interest. The data that they will take ownership for is the data whose key matches this key expression, and the key expression are used to route, query, and consolidate, obviously, data transparently for the application. But we will see this in some demo. We also provide a form of distributed computation called eval, and this is built on top of the Xeno Net queryable. Evals allow you to represent anything from a computed value to potentially a map reduce or even a voting. Okay, and again, that's how deciding how you want to trigger the computation. But that's a single abstraction at the protocol level that we use to implement or show you how to implement this kind of added value services at the Xeno level. Okay, so just in summary, what is the key difference between Zenoh and Xeno Net? So Zenoh is a framework that leverages Zeno Net Primitives to provide you an opinionated implementation of PubSub, geo-distributed storage, and distributed computation. Xeno Net is a zero overhead networking protocol that provides you with composable primitives for PubSub and generalized distributed queries. But for instance, Xeno Net, if you just use Xeno Net, well, you have to implement storages yourself, or you have to comply with the assumption taken by Zenoh if you want to use the storage implemented in Zenoh. Okay, that's also something that you can do and something that we strive in terms of interoperability between the Xeno Net and the Xeno layer. But you have to comply with the, let's say, the decision that we took at the Xeno level. But you don't have to agree with us, right? You can still leverage Xeno Net and the Xeno Net power potentially to build another geo-distributed storage implementation. In terms of API, we have API today in C, OCaml, Python, Java, Go, console, and obviously Rust for the new implementation. And for Zeno, this is how it looks like. I mean, the API is super simple. It's much simpler than Xeno Net, but here you have in a single page a publisher, a subscriber, and a query. I don't even need to explain it, right? I just want to highlight that you can even write primitive values, right, like integers or float, and that's dealt automatically. And here you see a query, in fact, yeah, a query being triggered, okay? So,
sorry, Angelo, for
yeah.
interruption, but I think our time is up now since we have to prepare for the next session.
So I'm ready for the concluding remarks.
Perfect, perfect. Thank you so much again for participating. Thank you.
So, by the way, you can try this online. And concluding, okay, so I think Xeno Net as a protocol is probably the most innovative and efficient networking protocol available on the market today. And Zeno is the only framework that, as of today, provides you with a very easy API to deal with data at rest, data at motion, and distributed computation. So thank you very much for your attention. And obviously, as you saw, Zeno is an Eclipse incubation project, and you can find more information on zeno.io. Thank you.